Hi, my name's Honda, and this is Threshold in China, a segment that gives you a taste of the future before it actually happens. I'm going to talk about emerging technologies that have life-changing potential and assess their ability to influence our lives in the near future. I rate these emerging technologies on a 1 to 5 scale across 3 different dimensions: readiness, novelty, and potential impact, or ripples as I call it. If a technology scores a 3 or above in all 3 dimensions, it reaches the threshold of potentially having a substantial real-world influence in the near term. The star of today's story is a bionic manta ray robot. When it comes to bionic robots, you may have seen Boston Dynamics' famous robot dog online, which moves and reacts in a way that's more lifelike than ever. Recently, there's been a Cambrian explosion, if you will, of bionic robots under development, and I have little doubt that we will increasingly see them in our living and working environments in the near future. Walking robot dogs on the street may not be such a novelty these days anymore, but diving with your own robotic manta ray would certainly reward you with quite a few thousand additional TikTok followers. Recently, a team of researchers from Hangzhou's Westlake University, led by Professor Cui Wei-Cheng, has launched an experimental robotic manta ray, capable of moving freely and quietly like a real fish, and submerging to depth well out of reach of human divers, enabling scientists to explore the wonders of the deep sea. We all know that the ocean is one of the last remaining frontiers on Earth for exploring resources for sustainable human development, as well as mitigating the impacts of climate change, assuming we have the proper means to explore its depths in an efficient and economical way. Professor Cui was the designer of the Chinese manned submarine Jiaolong. Since humans already have existing manned and man-made submersibles that can dive to the farthest depth of the Mariana Trench, why do we still need to mimic marine life? Well, by nature's standards, existing submersibles are rather clumsy, as well as loud and unnatural. The constant noise of propellers and engines cause many problems for marine life in the ocean. By comparison, real fish smoothly glides, swims, or wiggles. After all, evolution is the world's ultimate engineer, and it has almost 4 billion years of experience under its resume. The fastest known marine species, the sailfish, can swim up to 70 miles per hour. By comparison, the fastest known man-made submarine, the Project 661 Anchor, has a top speed of only about 50 miles an hour. Moreover, fishes thrive in places in the deep ocean that most robots cannot efficiently reach. And there's an extra bonus that comes with fish-like movement. Most underwater sonar systems were designed to detect the sounds and vibrations of conventional propellers and engines. So underwater vessels that mimic the natural movements of marine life can blend into the background noise of the ocean with far greater ease, and thus are much harder to detect. This could provide a critical advantage in maritime defense applications. That said, there are thousands of species in the ocean, so why mimic the manta ray? Well, the manta ray has the biggest pectoral fins in proportion to its body. These fins enable the manta ray to glide long distances with minimal effort. This kind of motion gives it the advantage of better mobility, stability, and concealment. Scientists found that manta rays can travel long distances vertically. In other words, they're very good divers. By changing the angles of the fins relative to the body, they can dive or ascend easily in the water. And for this reason, in the last decade, scientists have been trying to replicate their movement with robotic copycats. However, earlier models produced more zombie-like fishes, with rigid bodies and uncanny stiffness that would scare even the ghostly manta rays themselves. So when creating his latest model, Professor Cui and his team chose to tackle 2 main design challenges: flexible materials for the pectoral fins, as well as modularity that enables the model to be expandable in function. The first challenge is self-evident. Past robotic models of manta rays were made of rigid material. Traditional motors and rigid structures could hardly mimic the natural deformation of the manta ray's pectoral fins. So the team started by redesigning the fins. A real manta ray's pectoral fins is made of cartilage, muscle, and skin. It's structured like a bird's wing, except that manta ray fins have flexible skin. Cui's team custom designed a set of flapping wing-like pectoral fins made with 3 different materials that combine to mimic the wide pectoral fins of real manta rays. Carbon fiber is used as the underlying support structure, and lightweight polymers are 3D printed to form the shell and an inside layer so as to adjust to the buoyancy of the pectoral fins with a specific strength. The remaining 2 layers use liquid silicone compounds that have optimal elasticity for the use case. In sum, this is a process in which soft materials replace rigid materials, and 3D printing replaces forging, welding, and casting technologies. I have no doubt that this change will incrementally push the boundaries of robotic technology. But one other noteworthy achievement here caught my attention even more, which is its modular design. The past models of robot manta rays are like a flip phone of the old days. You can make phone calls or text with it, but not much else. You can't download apps on it and start surfing the web or social networks. You can't use it as a translator when you travel, or check out the latest viral videos. Those past models have just one or two fixed functions that can't be changed or expanded upon without redesigning and rebuilding a new model. On the other hand, Professor Cui's team made their robotic manta ray more like a smartphone. Like Android phones, they chose an open source design for both the software and the hardware. Inside the main body, there's a control unit, power unit, communications, cameras, and other sensors, all of which are easy to install and disassemble. You can assemble the robot fish according to the needs of the specific mission at hand, as well as the oceanic environment in which it operates, just like assembling Legos, if you will. Consequently, this robot's use cases are readily expandable. After the robot was assembled, Professor Cui's team tested its performance and yielded some promising initial results. Its flapping wing propulsion produced roughly 32% less drag relative to conventional propellers, while generating significantly greater lift for the robot. That means the flapping propulsion can be more energy efficient relative to conventional submarines traveling at the same speed, or travel far greater distances with the same amount of fuel. Compared to other existing man-made manta ray-like prototypes, Professor Cui's robot is by far the largest and the heaviest, while its swim speed comes in at about the middle of the pack. So while it's not the fastest prototype out there, its relatively large size and weight, along with its modularity, enables this model to carry an array of sensors for real-world applications, as opposed to just lab demonstrations. So this manta ray robot seems to be a promising tool for ocean exploration in the future. But how good is it according to the standards of the threshold rating? Well, let's come back to the three elements of the threshold rating system: readiness, novelty, and potential impact, or ripples as I'd like to refer to it. The readiness category refers to the maturity of a technology, from lab demonstration, a score of 1, to mass production, 5. The novelty score refers to how new the innovation is. 1 means small differentiation to existing tech. 5 means the innovation fulfills a brand new function. And finally, the ripple scale, as I'd like to call it. This is my opinion of a technology's potential for life-changing impacts and how widely it can be applied elsewhere. For more details of the rating system I'd like to use, you can pause the video here and have a look for yourself. So how does this manta ray robot stack up? Well, in the readiness category, I'd give this a 3. This prototype clearly goes beyond a demonstration of basic principles in the lab, but it's not yet ready for mass production at a reasonable cost. Nevertheless, this is a fully functional prototype. One of the downsides of the current prototype is that it's connected to a topside computer via a cable for control. Ideally, for real oceanic applications, some kind of wireless remote control mechanism needs to be incorporated into such a model. Better yet, as Professor Cui suggested, AI could be applied to the robot for control and navigation purposes. Next comes the novelty criteria. The flexible material design and the modularity of the system results in a clear functional difference compared to other manta ray-like robots, due to the size and weight being propelled in the water. So this goes well beyond small differentiation. However, it's not yet fulfilling a new function that can't be fulfilled by other technologies. After all, we have all kinds of submarines for underwater exploration, even if existing models are less efficient in certain ways. At the end of the day, the major component differences of this model gives it the potential to make undersea exploration far more efficient. So here again, it earns a solid 3. And finally, the ripples rating. The potential of this design to propel a bigger and heavier payload and to carry a variety of devices could make it a useful platform for a range of underwater use cases. Moreover, if material flexibility and modular design can be applied to the biomimicry of manta rays, similar techniques could also be applied to mimic the movements of other types of marine species from maritime vessels, and eventually other species outside of the ocean as well. This is a small but important step that opens up all sorts of new possibilities. So here I think a 4 rating seems to be reasonable. So at the end of the day, we have 2 3s and a 4. And that meets the criteria for real-world influence. At a fundamental level, what Professor Cui's team demonstrated here is our ability to make future robots mimic the physical movements of living beings in ever more nuanced and precise ways. If these techniques can be replicated, improved, and scaled up in cost-effective ways, It could enable a range of life-changing applications. So imagine a more lifelike prosthetics for disabled people who are missing limbs. Prosthetics which move and feel more like a real arm or leg. What about lifelike robotic cats and dogs for those with pet allergies or simply don't want the expense and hassle of a real pet? And of course, if you're a fan of dystopia and sci-fi like me, there are a whole host of military use cases for this type of biomimicry. For example, a reconnaissance drone can be designed that mimic the movements of the common swift, a migratory bird that can glide in the air for multiple months without landing. Or better yet, a human-like Terminator infiltration robot. So what new use cases can you think of for this innovation? We look forward to your feedback and thoughts.